Hi, I'm Joey Walker, and here's my analysis of the Mastering the Game of Go papers produced by DeepMind. In giving an overview of these two Go playing programs, I find it necessary to review their architectures, or how the neural networks are set up in the design of the programs. I also want to show the different ways in which AlphaGo and AlphaGo Zero were trained, and then I'll go over how they each make decisions when playing Go and the results or accomplishments. To start out, I'll give a brief history of Go and DeepMind. Go is a classic zero-sum game played between two individual players. A zero-sum game means that one player's gain is equivalent to the other player's loss. Go also has perfect information, which means the state of the game can be represented completely and accurate in data. This feature enables self-play. The optimal value function is an intractable problem in Go because the depth and breadth are so large. This makes it infeasible to create a perfect Go playing agent, but DeepMind attempts to search for an accurate approximation of this value function. DeepMind is a company founded by Demis Hassabis, Shane Legg, and Mustafa Suleyman in 2010. It was acquired by Google in 2014 for $500 million. DeepMind had previously created chess playing AI, and David Silver, who led the AlphaGo team, wanted to create a similar program that could achieve superhuman Go playing ability. AlphaGo is the first of the Go playing programs published by DeepMind. It is titled Mastering the Game of Go with Deep Neural Networks and Tree Search and was authored by David Silver and the rest of the DeepMind team. It was published in Nature on January 27, 2016. In the paper, DeepMind introduces a Go playing agent, AlphaGo, that utilizes a new search algorithm that combines Monte Carlo simulation with their value and policy networks. The AlphaGo program was the first Go program to defeat a human professional player in a full-size game of Go, when it defeated the European Go champion by 5 games to 0. The architecture of AlphaGo is built using two deep neural networks. The value network is used to evaluate the quality of board positions. It outputs the weights of the best board positions given the current state and the input features. The weights are calculated by the probability of winning after a decision chain that is cut off at a certain depth. And then the policy network selects the actual moves that AlphaGo plays. The policy function maps the probabilities of winning each action given the current state. The input into these two networks is a 19 by 19 by 48 matrix that stores the game state and the results if a move were to be made in a certain action. This image illustrates how the policy network calculates the percentage of winning from a chain of decisions and how the value network searches for the highest probability of winning each game. And then this table shows the input to each neural network. AlphaGo was trained in two stages, and this is also illustrated in this image. In the first stage, a supervised learning policy network was combined with a rollout policy network that could rapidly sample actions during rollouts. The supervised learning policy network was a 13-layer neural network that was trained on 30 million expert human Go positions and moves. Supervised learning allowed for fast learning because it could immediately update the weights of the network with high quality gradients. Another stage is needed because these networks only learn to play Go like a human. They do not have goals and cannot find creative moves. The training from the first state was transferred to the second stage via policy gradient. In this stage, a reinforcement learning policy network was trained through self-play. This allows it to experience new moves and focus on a goal. In this case, the goal is winning a game of Go. It does not matter about how much it wins by to AlphaGo, just that it has the highest chance of winning. The value network observes the self-play games of reinforcement learning policy network against itself. It predicts the winner of the games and it updates its predictions based on outcomes. So how does AlphaGo combine its knowledge from the reinforcement learning with the predictions of the value network? This is done through Monte Carlo tree search, and this is how AlphaGo plays Go. AlphaGo uses Monte Carlo tree search to combine the policy and value networks to select the action with the greatest probability of winning. It does this by estimating the value of each state in a search tree. As more searches or simulations occur, the search tree becomes larger and therefore the values become more accurate. The policy used to select actions during search is imposed over time by selecting later moves with higher win values. The Monte Carlo search tree will converge to the optimal value function with enough simulations. So when it's AlphaGo's turn to play, it uses Monte Carlo tree search to find the best action given the current state of the board and its policy and value networks. So here are the accomplishments of AlphaGo. On the table on the left, you can see how AlphaGo was able to defeat the European Go champion in formal matches. AlphaGo, when trained with the full distributed compute power, was also able to beat all previous Go programs 100% of the time. When trained with just 8 GPUs, it was still able to achieve the highest ELO rating among Go programs. Now moving on to the AlphaGo Zero paper. It is titled Mastering the Game of Go Without Human Knowledge. It was once again authored by the DeepMind team led by David Silver. It was published on January 19th, 2017 in Nature again. A quick overview is that this time around, the team at DeepMind developed a Go program, AlphaGo Zero, that is not trained on any human Go data. It is using pure reinforcement learning and self-play for training, and it had excellent results. To quote the paper, it says, AlphaGo Zero achieved superhuman performance, winning 100-0 against the previously published champion defeating AlphaGo. The architecture of AlphaGo Zero is a little different than AlphaGo. Whereas AlphaGo uses two neural networks, a policy and a value network, AlphaGo Zero uses a single neural network to evaluate its position. This neural network uses look-ahead search or the Monte Carlo tree search inside the training loop, which resulted in faster improvement and precise learning. A loss function on mean squared error is operated on by a gradient descent algorithm that adjusts the parameters of the neural networks. These parameters are nonlinearities or discovered features in the program that are input along with a state into the neural network. The network outputs the move probabilities or the probability of selecting an action. It also outputs a value or the probability of the current player winning from each state. As stated previously, AlphaGo Zero was trained purely on self-play mechanisms. Since there was no supervised learning to start with, it had to start from random play without supervision and develop its own strategies to win the game. Starting from human level play put a bottleneck on the ability of the original AlphaGo to find the optimal actions in its play. When it starts from random and always had a goal of winning, it can develop its own strategies. In each position, as AlphaGo plays against itself and Monte Carlo tree search is executed, this is shown in the figure on the left. It searches for an optimal solution to a certain reduced depth in the tree. Derelict noise is added to increase the frequency of exploration by AlphaGo. If it only relied on exploitation of what it currently knows, it could get stuck at the local maximum in performance. Exploration is what makes AlphaGo Zero feel creative in its play, and it sometimes makes it seem like it makes mistakes, but they are really just innovative new strategies. AlphaGo Zero plays Go similar to AlphaGo in that it uses a loop of searching lower levels via Monte Carlo tree search. The neural networks take the state as input and outputs and probabilities of winning from each state. The MCTS simulations use this to decide which move to play, as they go through lower layers and then come back up repeatedly, and then they finally play the highest probable action. AlphaGo Zero was able to achieve superhuman performance in a relatively short amount of time. In just 36 hours, it was able to defeat AlphaGo Lee, which was a later version of the original AlphaGo that beat Lee Sedol, the champion Go player. AlphaGo Lee was trained for months on much more hardware, while AlphaGo Zero only used 4 TPUs. After its full training, AlphaGo Zero was able to defeat the best version of AlphaGo 100-0. This is true state-of-the-art Go playing program. Here are my sources used in this analysis. The two Mastering the Game of Go papers by DeepMind, and then also the AlphaGo documentary created on DeepMind's YouTube channel.